Continuing our discussion on covalent bonds, this diagram shows some of the things that I said in the last slide or at the end of the last part that I think will help you understand some of the things I talked about. So focus first on the left side of the slide under A. And what this is trying to do is show you the electron distribution in this sharing between hydrogen and chlorine. And the darker the green is, the more time the electron is spending in that particular area. And so what you see is a darker green area around the chlorine and a lighter green around the hydrogen. And the small black dots are supposed to indicate where the nuclei for the hydrogen and chlorine reside. And what this sets up is a higher density of negativity around the chlorine nucleus compared to the hydrogen nucleus. And this can be depicted in this way with an arrow, and the arrow points in the direction of higher electron density with a little crosshatch, which in some ways is indicative of a positive sign. So you can see that this is somewhat positive on this end and negative on this end. And this is one way to represent it. Now, B is the other way to represent it. And these Greek lowercase delta, or D, show you which end of the molecule is positive and which end of the molecule is negative. And this is what is meant by a polarity or a polar bond. And so hydrochloric acid, which is what this is, would be seen as a polar molecule, and a solution of this would be seen as a quote-unquote polar solvent. And so when I spoke about water being a polar solvent, it has the same sort of situation as the hydrochloric acid. Now, covalent bonds, substances that have covalent bonds, can exist at room temperature as any of the following: gases, liquids, and solids. But in general, the binding forces, the intermolecular forces in covalent bonds are much lower than ionic bonds. And so if a solid exists, it tends to have a low melting point. And the gases and liquids are much more common when there's covalent bonding occurring. The liquid state, because the electrons are shared and they're not free to move around, it does not conduct electricity. Neither does the solid state, for that matter. And covalently bonded substances are frequently used as insulators in the solid state. Most of these are insoluble in water. If they're very polar substances, they can dissolve in a polar solvent. But in general, substances that are made out of covalent bonding result in things that are not soluble in water or other polar solvents. The solutions of these substances also do not conduct electricity. So for example, an example of a substance that will dissolve in water but has covalent bonds is glucose or sugar. You can dissolve sugar in water and that will not conduct electricity the way salt and water will. However, if you want to dissolve these in a nonpolar solvent like benzene or an oil, they frequently will dissolve quite well in the nonpolar solvents. Now, the other thing that can occur is you can have more than one bond. You know, if you share one pair of electrons, then you have a single bond. If you share two pairs of electrons, you can have a double bond. If you share three pairs of electrons, you can have a triple bond. And so the sharing, different kinds of sharing can occur in an attempt to fulfill that rule of octet, which is sort of overarching all the interactions that occur. The last of the three types of chemical bonds is the metallic bond. The metallic bond occurs when multiple atoms come together, and is called a metallic bond because it frequently occurs between metal atoms. These atoms come together and they just dump their electrons, their valence electrons, into what's known as a electron sea, or a common pool of electrons. And the electrons become delocalized in such a way that you can't really tell. If you could see the electrons, you couldn't tell whose electrons are whose once they're in this electron sea. This is a form of sharing, but it's different because the electrons that are shared do not stay with the atoms that contributed them. These electrons become totally delocalized in the solid. And it, like I said, it usually is metal to metal atom interaction. And these metals have similar electronegativity, but instead of a higher electronegativity of nonmetals, it's similar and low electronegativity. So for example, an iron bar represents a bunch of iron atoms that have come together and they've all dumped their valence electrons into this electron sea. Now, because it's all made up of iron atoms, that the electronegativity is the same or similar, in this case the same, but it's low because it's a metal. And these electrons then become delocalized. So the properties of the metallic bonded substances occur because of the delocalization of electrons. So let's look at a picture of this. First of all, let's go over the properties. Because the electrons are free to move, these things conduct electricity quite well. So copper wire or an iron bar or various other types of metals, alloy metals, conduct electricity usually very well. They also conduct heat because they allow for a lot of freedom of movement. They are what's called malleable, which means they can be hammered into shapes, and ductile, which means they can be drawn into wires. You can heat them up and pull on the two ends of an iron bar and it will stretch into a wire if you pull it far enough. The metals or metallic bonds are associated with substances that are frequently shiny when polished and reflective. And they have a high melting point and a high boiling point, which means that because of the way the electrons are shared, the forces are very interactive, and the atoms are held together in a very strong fashion. Now this is a diagram I wanted to show you. This sort of shows you A represents a piece of AU, which is gold, and it shows the gold nuclei as little yellow circles with a plus sign in the middle. And what it's trying to show you here is the fact that these electrons are delocalized. They can go anywhere they want, and they're coming from one atom and flying around to another atom. And what it also intends to show you is the fact that other electrons can go right through here without any difficulty, which is why it conducts electricity very well. And this is also shown on the right here with what's called B. You see that on the left of this figure B, the electrons are being introduced on the left side and electrons are leaving on the right side, and so it conducts electricity right straight through without any difficulty. The right side, those little plus signs are headed from right to left, and then the negative electrons are headed from left to right. Heat, it shows that if you introduce heat, there's freedom of motion with the molecules, and so it quickly conducts that motion down from one end, from the left side to the right side. And then D shows how if you put some sort of stress, and we talked about these various stresses such as torsion and deformation and so forth, that the nuclei will shift, and that's why you can bend bars and why you can hammer them into shapes, but they stay together even though they will bend. And this is another example of the delocalized cloud of electrons around the positively charged metal ions. Now we'll finish up. We may have to go into a third part to finish this, but we're going to talk about Lewis symbols. And you need to learn how to draw Lewis symbols. And I've provided you with a handout that gives you examples and also gives you some problems on how to do Lewis symbols. So this represents what happens, or the Lewis symbol of what happens in an ionic bond. And what you see is the atom of sodium with its one valence electron. That's the Lewis symbol for a sodium atom. The symbol of Na with a single dot is the Lewis symbol for sodium. And then the sodium cation is represented as a sodium with a plus sign. And the Lewis symbol for a calcium atom is the symbol for calcium, Ca, with two dots, because there are two valence electrons for calcium. And then the calcium cation loses both its electrons, so it's shown as a Ca2+ with two electrons available. Conversely, if you look at the Lewis symbol for chlorine, chlorine has 7 valence electrons, so it's the symbol Cl with the 7 dots around the outside. And then if you add the electron, presumably from the sodium above, then the chlorine anion is then formed with 8 dots and a negative charge. Now remember, sodium with a plus sign, the underlying shell of electrons is happy at 8, but you don't show that. But you do show it on the chlorine anion. The sulfur here is the symbol S for sulfur, and 6 dots, which represents the 6 valence electrons around the sulfur atom. You add the 2 electrons, again presumably from the calcium above, and you form sulfur with 8 dots around the outside. It's the sulfur anion. So here's some examples of how to draw Lewis structures for ionic bonds. I want to be very clear that you need to do it exactly like this, with the parentheses and showing the 2 ions. This is the way it is done. So you start out, here's sodium chloride, it is the top one. So you have a sodium with a dot, so that's the sodium atom, plus a chlorine atom, which is a chlorine symbol with 7 dots. These come together and you have a sodium with a plus, represents the sodium ion, and inside brackets you have a chlorine with 8 dots and a minus, and that's the chlorine anion. The second one is magnesium, the magnesium atom, the symbol Mg with 2 dots for the 2 valence electrons, plus oxygen atom, which is the symbol O with 6 dots for the 6 valence electrons around oxygen. When they come together, forming an ionic compound, the magnesium loses its 2 electrons, so it becomes Mg2+ cation, and the oxygen gains 2 electrons, it becomes O2- anion. And you need to have those brackets around there to show that come together that way. The bottom one just shows you when you have 2 electrons available from a single calcium, so you have to have 2 fluorine atoms in order to make the bonding complete. And so you lose an electron from the calcium that goes to 1 fluorine, and the other electron goes to a second fluorine, and you end up, notice the little subscript 2 outside the brackets on the right here. That means that there are 2 fluorine anions and 1 calcium cation. So the cations form when the atoms lose the electrons, and when that happens, you see that the dots go away. The anions are formed when atoms gain electrons, but also notice that the total number of electrons shown does not change. So for example, let's take the bottom one here. There's 7 electrons around a fluorine. 7 times 2 is 14, plus 2 from the calcium is a total of 16. If you look, there's 8 around the fluorine anion, times 2 is 16. So there are 16 on one side and 16 on the other. And if you look at the other ones, you'll see it works out the same way.